Good afternoon, good evening, everyone. We're just going to wait a couple minutes till we get to the top of the hour, and we'll get started soon. All right, number of folks are starting to join in, so I think we'll go ahead and get started. Hello everyone. This is Eric Ela. I am Director of System Operation and Electricity Markets with ESIG. ESIG also works with the Global Power System Transformation Consortium, or G-PST. And G-PST has a mission to bring together key actors across the globe to catalyze a rapid, clean energy transition at unprecedented scale and speed. This is being done by providing coordinated and holistic approach to the necessary knowledge, education, and support to power system operators across 5 action pillars. At the core of G-PST is a large cross-section of system operators from around the world who are dealing with a rapid transition from a system based on synchronous machines to one built around large levels of inverter-based and renewable resources. The 5 pillars of G-PST include research and peer learning, technical support, workforce development, standardization, and open data and tools. ESIG is the co-lead on Pillar 1. And if interested in more information on G-PST, you can go to www.globalpst.org. So ESIG would like to welcome you to this monthly webinar of our joint G-PST and ESIG webinar series, focusing on G-PST research agenda and associated topics, particularly those being addressed in G-PST Pillar 1. An additional series of webinars on the other 4 pillars is also being provided on a monthly basis, as is the standard ESIG monthly webcast series. So again, globalpst.org. You can get, there's actually a tab to get involved there if you're interested, and also if you're not aware, ESIG the ESIG website has more information about ESIG, where you can get to by going to www.esig.energy. All right, so a few logistical matters before we get started. Lines will be muted for the duration of the webinar. For Q&A, we will use the Slido platform, slido.com. So instead of writing questions on the chat, you can actually go to slido.com, enter in the code ESIG7 on the event code that you see on the screen, and then you can add your question there, and you can upvote certain questions you see that you think are important to highlight, and so forth. And I'll just remind folks to be professional, to focus on questions as opposed to, commentary that aren't really questions or anything like that. Just try to keep those to questions that you have interest to hear from the speakers on. We'll try to save about 10 or 15 minutes for the Q&A at the end, and then wrap up at the top of the hour. So today's topic is on the use of AI for tackling the increased complexity in power system operations. So as you might imagine, the changing nature of the resource mix with retirements and the addition of inverter-based variable and energy-limited resources, the explosion in data and complexity of modern power grids, many aspects of system design and operation are changing. So system operators have the critical function of keeping the load and generation in balance on a minute-by-minute basis to maintain a stable and reliable system. So today's webinar will provide an overview of key AI trends and technology that can be used for improving power system operations. Bringing that, a lot of times in the ESIG community and the power system industry, we hear a lot about the challenges of AI and what it's doing to consumption and how we have to prepare for that massive increase in load that comes from AI. But here we're going to more focus on how AI can be a benefit to a lot of the applications that we've been using for many years, especially applying AI to power system operations problems. So we're going to hear from Michael Walsh, CEO and co-founder of a startup working on these AI applications called GridZero.ai. And Michael will be joined by Ritesh Madan, who is a co-founder of the company, as well as Ian Kennedy, who is the Director of Innovation at EirGrid, which is the transmission system operator of Ireland. So Michael's been working in the industry for many years across many different industry organizations, and Ritesh has developed AI native products across a range of large technology companies and startups. So I think with the knowledge and industry background of this group, I very much look forward to their leadership and looking forward to hearing what they have to say. So again, just a short reminder to use Slido, slido.com. I think you'll see the link there on the chat, and the event code of E67. So with that, let's go ahead and get started. So I believe Ian will be kicking us off today. So Ian, over to you.
Thanks very much, Eric. And if we could go to the next slide, please, that would be great. My name is Owen Kennedy. I'm working with EirGrid. I'm the Director of Innovation and Planning with EirGrid, which is a commercial semi-state company in Ireland. And we have a very broad range of roles and responsibilities. We're the designated transmission system operator in Ireland, and together with Sony, which is the system operator in Northern Ireland, we also operate the single electricity market across the island of Ireland. We also own and operate the East-West HVDC interconnector, which connects to Great Britain, and we're developing the Celtic interconnector, which will link Ireland's electricity grid to France. And we're also going to be the designated transmission system operator and transmission asset owner of the Ireland's offshore electricity grid once built. So I'm delighted to be here today, or this evening. Michael, who you'll hear from very shortly, has asked me to provide some context and to set the scene a little bit in terms of some of the challenges being faced by TSOs, and then the need to, I suppose, explore and embrace new ways of working and new technologies in order to manage those challenges. In Ireland, as in many other jurisdictions or countries and markets around the world, we have ambitious decarbonisation targets, and we're seeing a really radical transformation of the Ireland and Northern Ireland power system at the moment. New HVDC interconnectors, new large amounts of wind and solar generation in particular, new storage technologies, lots of demand side response, quite significant demand growth due to electrification and economic growth, new system services, new network technologies, and the integration of all of these, I suppose, is increasing the complexity of operating the power system. We see very different conditions from day to day. If it's a windy day or if it's not a windy day, you have different voltage profiles, different load flow profiles, and I suppose the integration of inverter-based resources like wind and solar changes the characteristics of the power system in terms of stability management, and we have to be able to manage that. The variability needs to be managed as well in terms of managing things like ramps, for example, large ramp downs, perhaps in wind forecast while demand is increasing. There's a whole range of technical challenges which are set out on this slide. I'm not going to go through them all, And I suppose we have in EirGrid been developing tools over the years to help us manage that, the complexity. And we were capable of operating the power system with up to 75% of generation coming from non-synchronous sources like wind and solar, which has been fantastic. But I suppose looking forward to where we're trying to get to and operate, close to 100%, or up to 100% of generation coming from non-synchronous sources, that's going to take new tools, new capabilities to be able to manage that, if we're going to continue to operate the power system securely and in a resilient manner, which we're going to do. If we could go to the next slide, please, that would be great. And I suppose, in terms of this transformation, one of the things that's really clear is that there's a, incredible pace of change. I think the power system and the industry is changing faster at any point in my lifetime. There's a huge number of programs of work that we need to deliver across networks, across markets, across system operation. And I suppose traditionally EirGrid, like many other businesses, would have approached these kind of IT or software type projects using a kind of traditional waterfall model, where you set out your requirements, you go through the design phase into implementation, through to testing and go live. And I suppose in EirGrid we've been exploring new ways of working, more agile ways of working that will enable us to kind of more rapidly test, refine ideas, to get better insights into complex problems, and to deliver, I suppose, better, more effective solutions. And prototyping and working through prototyping in that process is a kind of a core area that we're exploring at the moment. And I suppose when we look at why now, I suppose we do need to deliver more quickly. That the pace is quite incredible. The complexity that's there that needs to be managed is increasing, and of course there's new technologies and new capabilities like AI that can be leveraged, and we're looking to try and leverage as well. So I suppose earlier this year we appointed GridZero.ai, who you'll be hearing from shortly, to undertake a sort of bite-sized small piece of work which looked at forecasting of the largest single in-feed and largest single out-feed at day-ahead stage on the island. And as a TSO, those largest single in-feed and out-feed levels are a really important input into determining the amount of reserve that we need to carry to manage disturbances on the power grid. And that's particularly important in Ireland and Northern Ireland, given the size of the in-feeds and out-feeds relative to the size of our grid. It's a peak of across the island of about 7.5 gigawatt, but like demand falls down to kind of just over 3 gigawatts. So it's a really important aspect for us. And we set out a case study, and I suppose Michael and Ritesh will talk a little bit about that case study, as well as some of the other work that they're doing in GridZero.ai. So I'll hand over to Michael now, who'll talk through it in a little bit more detail.
Thanks, Owen. So look, while Ritesh maybe is going to take us through the technical thing, we maybe move on to the next slide. Just a little bit about GridZero. When we started ourselves up first, our core philosophy is trying to combine leading AI and power system expertise, so that we're not just a hammer looking for a nail, that we're very focused on the understanding of the grid. But we'll take maybe Ritesh. Do you want to have a walk through some of the technology, and then I'll start covering the actual application and case study?
Yep, sounds good. Thanks, Michael. So forecasts and data obviously have been used by many players in the energy sector for a number of years. And classical point forecasts and classical machine learning models, they work pretty well when the training data distribution is very similar to the distribution that you're trying to for which you're trying to do prediction. So at inference time, whatever the distribution of the signals and the data is, as long as it matches well with the training data, point forecasts to predict load, predict prices, predict reserves, capacity needed, all of these forecasts work pretty well. But as the grid and the market has become more dynamic, with more renewables on the coming onto the transmission grid, more variability in weather patterns, and then that resulting in more action spaces for utilities and transmission system operators. All of these things lead to higher dynamism in the grid, where essentially the assumptions of the training data on which a classical ML model is trained, being the same as the time of inference, that actually starts breaking down. And that's where these models start breaking down and don't perform as well. And then when you layer on decision making, where you're making certain decisions a day ahead and then in real time, and all of that actually changes the distribution of data, you're actually just taking inference from one model, feeding into the next one, and then you end up essentially adding noise. So for this more dynamic interconnected grid, we looked at fresh approaches, and there's an example on the right side of the slide. So this is something that comes up across many players. So if you want to operate batteries at grid scale, one of the key obvious decisions is, should I charge the batteries or should I discharge the batteries at a given time? And classical way of doing this would be, you would look at forecasts of various variables few hours out and make a decision. The challenge with that is, as you take a decision and change the distribution of storage on batteries meaningfully, all the downstream signals have distribution of those downstream signals have changed, which means that the forecasts you had previously are no longer as accurate to predict what would happen downstream. And so it's very hard to actually optimize against classical forecasts. And what that ends up leading to is conservative decision making in terms of discharging batteries not very often and charging them whenever there's an opportunity, so that you keep them for reserves. So that's the kind of challenges you run into. Let's go to the next slide. On the other hand, as the grid is becoming more dynamic, the action space is increasing. As we all know, there's been a lot of activity in the AI sector over the last 2 to 3 years. There's lots of advancements, both in terms of model architectures as well as compute. And I'll just summarize some of those at a higher level and the ones which are pertinent for what is in the subsequent slides. So if you think about transmission grid and all the signals that go into and multi-horizon planning, these are all sequence decision problems where essentially you get certain information, take certain actions, and then try and estimate the impact of those actions in space and time downstream, and then take the next set of actions and so on. So very abstractly at a high level, these are sequence decision problems. And transformer models have been a big unlock in modeling such sequences which are correlated across multiple sequences in space and time, as well as capturing effects of what if analysis. And if you take certain actions, how will the downstream effect, sequences change? Transformer models are, they use deep learning to essentially provide highly accurate predictions of signals downstream, which are adaptable to new information coming in, adaptable to decisions that are made at time t, which affects everything at time t plus delta downstream. They're also powerful because they are these computational architectures are highly parallelizable. So compared to some previous generation of sequence models, transformer models are highly parallelizable, which enables us to actually train these models on a large set of data, bring all the data together, and then run inference really fast. And then once you put that together with all the advances in the GPU architectures, which are essentially hardware accelerators to do the kind of computations which transformer models and general linear algebra that's needed to make this technology work, the two put together really are a huge unlock, because the cost of inference goes down, the scale at which you can do inference, the pace at which, the latency with which you can actually do inference and training, all of that reduces dramatically. So when you bring those two together, they've driven a lot of innovation in multiple sectors leveraging AI. And on the right column, there's some examples. I'm sure GPT, Gemini, these are all familiar to the audience. These are text-based models which are training on all the data in the web, which are essentially sequence models of text, which, when you enter a query, predicts the next set of words in the sequence, which enables you to answer questions and keep going. But they're also being used in ads ranking, for example, to build foundational models to understand, which ads would do well with what kinds of audiences. They're being used in physical AI. Waymo and other self-driving companies have started using foundational models. Robotics, there are a number of startups actually innovating, building foundational models for robotics, as well as for modeling consumer behavior for pricing and promotion. So there are many consumer companies, to figure out what promotion to offer to which user under what condition to drive incrementality. They've been used to model consumer behavior as well. So these are just examples of some applications where, you know, what folks are doing at a high level is bringing all the data they have, putting them together in a common model, which then this model is highly adaptable, enables you to actually do reinforcement learning and ask what if questions, make decisions against these models, and then repredict and keep going. So they're using these model architectures to drive a lot of innovation. Next slide, please. So the approach we took in this project with AirGrid, and which actually makes sense, you know, as we apply AI to any vertical, is it's one thing to bring all the data together and train a black box model, but to really make it useful in a particular context, it's really important to understand, and this is one of the core philosophies we have at GridZero, and I've seen this in my previous life as well, is to understand that the vertical really well. And that's where the expertise in power systems and the folks actually working who would actually consume the outputs from this model, bringing that expertise in the loop is really important. So we did a couple of things. We essentially, first of all, brought all the data that we had access to from AirGrid, layered on additional insights. For example, the wind direction, the amount of wind in the UK changes some of the core flows on the interconnectors between the UK and Ireland. And so we brought in wind data as well to bear on the model. And then we got insights from the operations team, example, how much renewables are reasonable to run on the grid and what are the constraints that impact, you know, how much renewables can you actually run on the grid. So we brought in those insights and constraints as well and encoded those in the model. And over time, you know, after a couple of iterations, the model actually got to a place where it actually was usable for the application that we built, which Michael will cover in the subsequent slides. The core message here is, you know, it's a flywheel. As you build an initial model, bring in more insights, then you realize you need more data, bring in data, add the constraints, and then doing this 2 or 3 times, we're actually encoding the actual knowledge of the vertical into the model. That's what actually leads to really powerful models and helps us differentiate with respect to what may be the current state of the art. Next slide, please. And essentially where we are at the moment is through this flywheel effect, what we've done is we've essentially built a foundational model for the electricity system for Ireland while modeling some of the key effects of UK data. As well as some of you may know, the markets in Europe are becoming highly interconnected, where what happens in one market actually has a downstream impact on other markets as well. So UK was the most correlated for this application, so we brought in UK data. And what we brought in physical and market data. So physical data is, for example, the core flows on the network, some of the generator availability, along with market data, which is, you know, cost and pricing that affects essentially what happens in the market as well. So we brought in all of this data to bear on predicting the core flows, which is the application Michael will talk about. That's one of the labels we're predicting, but we have the ability to predict other labels in the market as well, which would be, you know, for example, pricing or bids that we expect downstream and so on. So we built essentially the core foundational model for a subset of the European market, and we're soon expanding to all other European markets as well. Next slide. I think, Michael, it's over to you. So Michael will walk through the first application that we built in partnership with AirGrid for this project.
Yeah, thank you, Ritesh and Owen. So Owen started describing the larger single in-feed and out-feed problem and its importance to AirGrid in reserve planning. And you can see on the lollipop graph in the blue box, that's essentially a graph of looking back on a historical week of what the larger single in-feed and out-feed were, just larger single in-feed, sorry, on that graph. The different colors represent a different unit setting. And so you can see it's multiple different units that are setting the largest single in feed at different times. So that might mean interconnector A has the largest flow at 9 a.m., but generator B is the largest in feed a couple of hours later. So it could switch around quite a bit between, probably any of the 10 largest generators and any of the 3 interconnectors. You can also see quite a large variation in what the in-feed is, varying from numbers up to about 500 megawatts down to as low as 200 megawatts. And when you think of what Owen was describing about, the impacts on reserve and system stability, that's a very significant up and down change in reserve requirements. And you can see it happening very suddenly and over very short periods of time. And you can even see cases where it dips down and then back up again. And that all points to how tricky this problem is. Essentially, Owen mentioned it's a 7 gigawatt island system, and your largest single in feed is between 200 and 500. So if you get maybe, a single, 200 megawatt shift in wind or in interconnector flows, that could move the LSI, LSO very significantly, very quickly. And in this case, we were trying to forecast it at 9 a.m. D-1. So 9 a.m. in the morning for the next trading day, which is 11 to 11 p.m. So essentially 14 to 38 hours out. Now, when you're doing that in the Irish sequence, 9 a.m. is before most of the big significant market events happening, before the generators have to put in their physical notifications, before you have a lot of the bids in for interconnector trades. There's 2 intraday markets that run between 9 a.m. and actual trading. So you're essentially having to deal with very early stage renewable forecasts, absence of physical notifications for generators. So there's quite an amount of data absent. And the brief here was to try and give EirGrid a view of what the LSI LSO would be at 9 a.m. to help them with the operations planning and to inform operations planning and reserve scheduling for the next day. So we move to the next slide, please. So first thing we did was an analysis based on, after assembling all the data, to understand what are the types of features that would impact on the largest single in feed and out feed. We then had a workshop with EirGrid to go through these, and a lot of them would have been what EirGrid would have expected, and for subject matter experts, quite obvious things like the residual load, which is the total amount of demand minus the renewables to be met, is the singlest influencer increasing it. Wind availability, all island is a big interfactor, but we're seeing slight differences in what the availability of wind in the north versus Republic of Ireland would have, and versus the all island data. So we can get quite granular in it. And some of these, when you work through a workshop with the EirGrid experts, they say, well, what about this other thing? And it may be that we weren't capturing the data, and things like residual load is a sort of it's not a direct variable, it's one minus another. And that was an insight that EirGrid, along the lines of Ritesh mentioned, help us understand that A minus B is a critical variable, and then we look deeper at that. And all of these insights help us to work through the process Ritesh described, where we're building a very purpose-built platform that understands fundamentally power system influence dynamics and uses that to improve the quality of the results. It also maybe gives a flavor of the type of interactions that we have once we're doing a project like this with the experts. We're not sitting down looking at long pages of equations and spec sheets for a software product. We're really getting into the meat of the problem and trying to get to the fundamental of what is the problem we're trying to solve. We're looking at the data, bringing back insights, talking about what those insights mean, getting deeper levels of understanding, using that to deliver the next phase of insights. And that's essentially the flywheel effect that Ritesh just described. And as part of that, you can see we added in wind generation in GB as one of the key influencers, because essentially a large change in wind in GB will have a big influence on the flow and interconnectors onto the island of Ireland, and they may or may not then set the largest single in feed. So it's a very important critical variable, and we were able, with the architecture Ritesh described, to quite easily integrate that into the model and make use of those insights. So just moving to the next slide, please. So these are the results of what we got. So in all 3 graphs, the green is the actual LSI that happened. So the green is essentially the bar and the target of what you're trying to hit. The top result shows our forecast in blue. So this was our prediction of the LSI as received based on the data available at D-1, 9 a.m. The graph below it, pink, is a simple schedule-based view of the expected LSI LSO at D-1. It's a very basic method of doing it, but when you're dealing with such an absence of data in terms of reliable, accurate forecasts, not having received market nominations or bids, you're essentially looking at quite basic ways of doing this. And the last one then is in red is the 8 hour ahead. There's a rolling 8 hour ahead prediction model used in EirGrid of what the actual unit will be. And this is essentially doing it with all the information that it's received from physical notifications, more accurate renewable forecasts, intraday trading windows on interconnectors, all those results, etc. So this is dealing with very accurate results. And what we see is that the results of our model were substantially better than the very basic schedule-based one. But that's I suppose, a slightly easy comparison because that method is constrained quite heavily. But we got within 1% of the 8 hour ahead method over the test period. And what that actually means is that with giving on a window from 14 to 38 hours out, we are giving you the same visibility as you get normally 8 hours ahead. And the idea is for an operations planning or an operator planning or someone that maybe if the user was, say, a flex provider or a generator or someone else, you're getting access to 8 hour ahead information maybe a day earlier in some cases than you normally would. And that gives you more opportunity to plan how you're going to schedule your reserves, how you're going to position your assets in the market, and various other decisions of what you're going to do. So just moving on to the next slide, I'll drill a little bit deeper into the components of this. So we also have the ability, as Ritesh said, to run what ifs. So let's say you've done this, but you're a little bit concerned on this case that maybe the wind is going to come earlier or later, maybe it'll be more or less windy. So we did an example where we said, well, what if the wind forecast was 20% higher or 20% less on a given day? How would that impact the LSI, LSO? And the first thing you can see is it's very nonlinear. It's not a one-to-one. As the wind gets higher, this is a pattern. So you see some, general things. The more windy it is, essentially, if you have more wind, you're using less interconnectors and large generators. So essentially, more wind will tend to lower LSI, which is what you'd expect. But sometimes it's the same. Sometimes it doesn't move it, and sometimes it moves it quite a bit. And that sort of talks to the nonlinearity of the problem and how various different things interact and change. And it shows as well that the model is learning those interdependencies. It's not just doing a simple scaling forecast. It's taking into account all the various different variables that we're in and using that to help you generate more insights. This has a very fast runtime based on the GPU architecture that Ritesh described earlier. So it essentially means that in an operating environment, these are things that an operator can just put in very simple queries, get quick results, quick answers, test hypotheses. And if you're looking at sort of a 9 a.m. doing reserve planning for the next day, it means the operator would have the opportunity to look at multiple different scenarios, test ideas, test interrelationships, get a sense of what's happening, what looks realistic, and then use that to risk assess the decision that's been made. And just moving on to the next slide, please. To do LSI, LSO, you have to look at an awful lot of variables. It's essentially you're saying, well, what is going to be the largest single infeed? It could be any one of 3 interconnectors or potentially 10 large generators. It's going to be heavily influenced by the wind, by demand, etc. So when you actually dig into it, where our maximum objective and that we're trying to do is get the LSI right, but you've also got all these sub variables that you can drill into and look at the expected flow on various different interconnectors, output of large generators on wind. And you can also look at the what if analysis and what it's going to do for those. So you can see in this case, with the 20% more or less wind, you can drill into an individual interconnector here, and you can see again the same effects we had, that in general the trends are as you would expect. But again, it's not a consistent linear offset. You're seeing very big changes on one day, but on many other days, it's quite low impact on the flow on that interconnector based on the degree of wind. And that speaks to, I suppose, giving you more insight into the system. And when you get the SME in the loop and you start digging into these results and talking about, okay, on this day, what was happening, what was different, you can figure out, maybe deeper understandings of the variables and and you can do graphs and explainability along the lines of the one we saw earlier to help you understand what's driving these behaviors, where are the correlations, and help to increase the insight the users and the operators have. And also to risk assess this so that it becomes a very reliable tool to use to help you with the day ahead planning. So just move to the next slide, please. So to give you an idea to just the flow of the project, It's a very fast, and we spent, I suppose, about a year building our core purpose-built foundational model. We benchmarked it on a couple of systems internationally, and put a lot of effort into getting it to perform well on various rounds of data. So when we came to this project, it was about a 6-7 weeks in total. But once we got the data cleaned and ready to go, we turned around the core modeling capability in about 5 weeks, including weekly feedback from the ERGRID team, where they were giving us maybe 2 hours a week in workshops where we were talking about, we were showing graphs, talking about results, talking about power systems, talking about impact. And essentially, we were able to have this done in about 5 weeks, and then get in the last 2 weeks with the advanced applications, where we built the what if functionality to test various different scenarios. And we also customized the user interface, and data integration strategy for ERGRID. So I suppose before I start handing back maybe to Ritesh for some final thoughts on the technology, and maybe Owen to get his reflections on the overall process, I do want to acknowledge the expertise of ERGRID. They were very open to using new technology, and they approached this with a completely collaborative approach. When we were in the meetings, it felt like a group of people getting around the table trying to solve a problem, talking about the actual issues, and very, very solution focused, and complete collective focus on trying to get the best result possible. It was very enjoyable, I think, from our team, and I think that collaborative aspect was part of the force multiplier that got us results that we were very happy with. So maybe Ritesh, do you want to share a bit of ideas of the future and where we go from here?
Sounds good. Let's go to the next slide, please. So this is a high-level diagram of how we're architecting the platform, and we built out some of the components, the core components here already. So if you take a particular market, and Europe, like we mentioned earlier, is becoming more and more a coupled market. So if you bring in all the data for Europe, it essentially forms a core data foundation that represents the market dynamics, weather predictions, the core physical signals around scheduling, flows, constraints. So that's sort of the solid foundation layer. And what we built on top is a foundational model, which is, takes into account all of this data across multiple time horizons, across different geographies, and across these different signals, brings that all in a common model. And it's the same model that we are using to enable different applications. So LSI prediction is an application Michael walked us through. But once you have the core inference model, the requirements for each of these applications and the timescale at which you do prediction will vary, but we can use the same model to actually build multiple applications on top. And the benefits of that is you can actually now start doing multi-time horizon optimization, where you can model the effects of decisions one takes 3 days out, for example, and include the impacts of those decisions in terms of the inferences which are run for to enable decision making in real time. It also enables more optimized decision making across different parts of the organizations, where as one part of the system improves, you get more data, you bring that back to the foundational model, which then helps improve decision making across the board. So this is, it's a more top layer is more loosely coupled to enable teams to work in parallel and do the day-to-day jobs, but they're all being powered by our vision is to power it through a common foundational model, which we've built the first version of. So that's how essentially we're architecting the platform at GridZero, and we're looking forward to enabling a lot more value across the whole energy system, electricity system. Over to you, Owen.
Yeah, thanks very much, Ritesh. I just I suppose to a reflection from the ERGRID side, and as kind of Michael mentioned earlier, it has been from our perspective as well, a very positive experience working with GridZero.ai, and this is very collaborative, as Michael said. That was what I heard back from the experts in ERGRID here, who are working side by side with the folks in GridZero.ai, looking at the iterative sort of kind of approach, that prototyping approach, and kind of learning as we went. I thought it was a really, really positive really positive experience. I suppose that opportunity, to kind of leverage these types of technologies is something that EirGrid is really looking to kind of develop and build on, and to kind of enhance those ways of working. There's a lot of focus here in EirGrid on building the foundations that will allow us to kind of go beyond what we have been doing. And things like the data management side, the data governance are really important. Having the tools and the platforms and developing those processes and ways of working is something we're really focused on. But yeah, a really positive experience. So so I'll hand maybe back to Eric.
Great, thanks all. So we've got quite a bit of time for questions. So I just encourage the group here to keep throwing in your questions there, and we'll try to get to as many of them as we can. And yeah, just keep adding them in there. So guys, there's a couple questions just around data and sort of what was used, what was most beneficial. So maybe the first one is just, and you kind of talked about, what some of this for that, the LSI, LSO application, what are, you touched on a lot of the different components that were, had the largest impact on that. So maybe you already really answered this, but yeah, so there's a question around what's the can you share more about a prioritized list of the data was used? Maybe another question, if that's sort of something we already answered, was given that AI suffers from historical bias with fundamental models, how are you addressing unseen and future system conditions as things change, trends change, things like that?
I can take a first shot at that, and then Michael and Owen, please chime in. So all models obviously have some bias built into it because they're using what we know to predict the future. But few things that we've really tried hard to do. One is really focus on random variability and stochastic effects in the system, which cannot be modeled, for example, through power system tools, where we know the physics really well and we have really good models to understand, for example, how voltage will respond to certain changes on the network. And Michael, I know, are more experts on that. But what we try to really use AI for is modeling correlated effects. For example, if you discharge a battery, that impacts your reserves capability downstream, which impacts your decisions downstream, which impacts all the participants in the market in terms of how they bid into the system, which impacts the price of acquiring energy downstream, which then impacts reliability. So there's a lot of probabilistic modeling that's involved in modeling these effects, because there's a lot of behavioral effects one needs to model across the system, along with random variations due to weather, etc. So that's where we're using AI. And what we've done is actually really focused on having the best-in-class learning rates. So that's where adaptability is really important. As fresh data becomes available and as we take decisions which then impact downstream effects, modeling the effect of our decisions as well as fresh data that comes in to compute the outputs of inference models, that really is key to making sure we are learning as fast as possible rather than being completely biased by the training data. And that's where transformer models have a step function improvement as well compared to previous generation models, where if you have a tree-based model, and we tried this back at Uber, trying to bring in real-time signals into tree-based model and making it adapt to changes in information is really hard. Those models are really not very adaptable to real-time information. You can do it. It takes a lot of feature engineering, takes a lot of work. But these transformer models really excel in terms of at least generalizing and using real-time information to adapt much better than previous gen models. Is there some training bias? Of course. I mean, the models have pre-trained weights, which are then essentially changing as new information comes in. But what we've seen is the models are actually pretty responsive to new information, and we can run what if scenarios. We can bring in new information to actually recompute the inferences, which then lead to more accurate inferences downstream, and then you can keep optimizing against that. So that's the sort of the high level answer in terms of how we're approaching to making sure we are least biased as possible, but at the same time getting the most value from the training data, which by definition does introduce bias.
Great. I think the next question maybe is somewhat of a quick yes or no in terms of maybe Michael, for you, if how much is transmission considered as in part of this, and does that make it more complex?
So yes, and yes is the answer to both of those. So we consider transmission to be, we don't do an actual network load flow model as a part of this, but there are various key constraints and ways of operating the system where you might have a minimum number of generators that have to run in a certain region, or there may be conditions that happen. And we do walk through those in these SME loops and see, well, where are they significant, not significant, and what are they driving? And particularly, we'd also go through, look, when did they change in the past? Because you may be seeing a big step change in the data where, but that could have been driven not by some fundamental market behavior, but by a change in operating policy. And by going through those sorts of things and understanding what the network was, how it evolved, you bring in more and more insight and increase the performance of the model. So yes is the short answer. We do include transmission. We do it, based on I would say not a very detailed load flow type approach, but more on a zonal type of approach, which we find for things like operating schedule is quite accurate. I might just like to build on Ritesh's answer from the last one as well. I think on a different project we were looking at day-ahead price forecasting in a market, and what we found when we compared it with existing models, where we got an unusual event, particularly high demand, high temperature event, so a lot of solar and also an increase in demand, and it had gone outside maybe the range of unusual conditions. We found it happened 3 days in a row in a given week. The first day it happened, both our model and the existing model missed it and didn't see it. But as soon as we got to the second day and our model had visibility of the first day's done, it did all the things Ritesh said. So it took in the more recent information and it adapted the context. And if you think of your experience, if you're using something like a ChatGPT, etc., it's trained on a huge amount of random data on the internet, but yet it manages to throw out really impressive, sensible results. And it takes very cognizant effect of most recent things it observed. And we're seeing the analogous thing happening in the power system, but on a much more constrained, high quality data set. And we are seeing the ability to respond to more recent trends and, particularly in unusual or conditions you hadn't seen before, the ability of these models to predict new and different things, taking account of the recent context, is radically better to what's available from existing technologies.
Thanks, Michael. I might throw in one of my own questions just because linked to the data, some of the previous data questions, and it's around probability-based data, and obviously with setting reserve requirements and with forecasting wind and solar output and load. A lot of TSOs around the world are using probabilistic information that's used as input to the traditional power system applications. And I'm curious how much of that data, given, assuming EirGrid might have that type of data, operational probabilistic forecasts, how helpful can that be to the training as well as for prediction?
Yeah, so
go ahead, Michael.
Yeah, I think maybe Owen, you might chip in a bit on the EirGrid side of it, but like essentially the beauty of these models and the way we do the collaborative approach is that type of data is incredibly valuable. So any information or insights that EirGrid could have or available, and even very often it can be know-how that a skilled operator has built up. We can drill into that and trying to understand, okay, well, what would you be looking for? Where would you be seeing that? And the beauty of these models is you can take all this and easily integrate it into a single platform. So whereas traditionally a model would be using, you'd use a very deterministic set of here's the data I'm going to include to collect this output. if someone says, yeah, but I always look at the weather forecast, or I look at this other thing and that influences me more than that, and historically I found this, we can just take those data streams and integrate them into the model and see, okay, yeah, now we've integrated that other data stream in, and yes, it is improving the results in the situations you described. So all these insights, information, extra data, any extra streams that an operator have, with the ability to integrate them, test them, see what they do, in what conditions do they improve the model, and essentially take things that people observed over many years and, you know, really start quantifying how they impact what conditions. And you know, our experience over this project is, you know, the cumulative effect of those is the model just keeps improving and improving the more you have those conversations and integrate, you know, whatever available data sources may be there.
Yeah, I don't have a huge amount to add. Michael, like, answered it very well there in terms of the sort of data. Like, we do in AirGrid have, you know, good renewable forecast data, for example, that comes in from third-party vendors that we use. That's got probabilistic bounds and so on, and information that goes with that. But to Michael's point, there was a lot of discussion back and forth between the two teams on what was available, what could be used. I think, Michael, you mentioned earlier as well about looking at the GB wind that came out of a conversation as well. And obviously, as Michael said as well, it was a relatively short kind of turnaround for the project of 5 or 6 weeks. So within that period, there was quite a bit of kind of iteration and learning and taking on board some of these some of the outputs of those conversations to enhance the model. But the guys definitely are the experts on the modeling side of this, not myself.
The last thing
Sorry.
that I add is our outputs are probabilistic as well. So we compute a mean prediction along with the distribution, which of course is relevant for reserves planning because you want to look at tails for actually planning reserves. So we output those as well.
That's I'm glad you mentioned that, Ritesh. The next question I was going to ask is around metrics for, you know, comparison, you know, to the benchmark. You're showing the I think the mean absolute error comparison to some of the existing methods, and yeah, the question here is, yeah, are there other? I guess maybe I'll kind of change the question slightly, but are there other metrics that can best demonstrate the value of this compared to, you know, benchmark, especially, you know, as you said, with the probabilistic outputs, maybe that's not really just a simple deterministic, you know, error value. And I'm just curious, you know, especially looking at, you know, if you get the extremes wrong, and other metrics that might be able to capture more of that data to really demonstrate the value compared to what we do today.
So we actually went one step further and did a simplistic headroom analysis. You know, if we were to use this model compared to the current methods being used, how much can you actually optimize reserves? So if you look at tail outcomes, for example, one of the reasons to look at tail outcomes is because the metrics that matter for each application are a bit different. So we actually tied it to the financial outcomes, and roughly, I believe we got 20. Michael, you may correct me if I'm wrong. 20% is the number I recalling from top of my head.
Yeah, I think it was 20. We did 20% was if we were to, you know, really squeeze it, and 15% was then if you're going to be conservative and sort of add a margin of safety, so that you're essentially not going to you know, try and reduce it to the absolute maximum, that you could do a 15% reduction in reserves. And that essentially takes into account, if you remember the graph that we showed on it, there was a gray band which we didn't talk about. That's essentially the 90% confidence interval around the forecast. So it sort of gives you the expected mean prediction, and we use that to do essentially the mean absolute error and the normalized mean absolute error. But we also did compared, well, okay, if you were to essentially just use the top of the confidence interval, so you're taking a conservative approach for reserve forecasting, and you use that as the amount you reduce reserves by, how much could you save, and what would the security impacts be? And we were going through a layer of analysis of, okay, in what circumstances might that, and how much time would you have to go and re-optimize if that. again, it's quite a detailed analysis, but the short version was, once you start looking at this for something like, say, a day ahead operations planning application, you do get yourself the ability to save quite a bit of money when you look at those metrics. But you also look at, okay, what's my risk assessment? So say I get it wrong, what warning, how can you run the model and give yourself time to essentially reschedule it, and how often is that going to happen, and what will the cost be? When you look at that then over an annual basis, you find, okay, over an annual basis, you're going to save quite a significant amount of money, and you can put in the safety guards and automate the operational procedures such that you're never taking any increased risk over and above what you're taking in the base case. Now, there's a bit of detailed operation planning, and a lot of this, once you get these new tools that give you improved functionality and visibility of data, you have to, really work through a lot of, take a very thoughtful approach with an operator to say, well, how are we going to actually use this and turn it in? And to your point, we can do any metric under the sun. That's just statistics. It's easy to do them. What's important is to think, well, how is an operator actually going to use this? What would they be? Because there's no point in us saying, well, we could save X% if we did it this way. If an operator says, yeah, but there's no way I would ever chance that, it's too risky, but here's what I might be comfortable doing. Say, okay, well, let's write that down, make that our metric, and see how we can, make the model perform best to give you, information that's usable to you and that you're comfortable with to actually improve your experience.
So, kind of following on to that, and I think there's a couple of questions around like impacts, financial implications and maybe reliability implications. But I think that all kind of goes into like, okay, another metric is trust, amount of trust from, system operator. We know that system operators are by nature conservative, are like to use the methods that they're familiar with, that they have the trust in. So, and of course with AI, somewhat of a black box to a lot of us, and understanding like what's going on, what comes out of this. So maybe starting with Owen, how does sort of the, especially kind of the operator perspective, how do you sort of overcome that sort of trust barrier that's often seen in using AI for applications such as that can have large reliability implications associated with what comes out of the output?
Yeah, great question, Eric. What I would say is that we're prudent rather than conservative in terms of the decisions we're making and the approach we take. But I suppose in terms of AI, I think there's a piece here around getting comfortable, to your point, around being able to trust what we're seeing and what the models are telling us. And I think for us, certainly this project as a really good pilot has kind of is helping to do that. It's helping us to kind of build our understanding and our capability of what these types of technologies and AI can do to support us. I think there's lots of capabilities that may be deliverable down the road. For us, initially looking at things like forecasting is probably an area of where this type of capability can really be very positive in terms of informing decisions down the track, etc. So there is a piece here about kind of developing an understanding of how it can help us, and doing it in a way that we gradually build up our capability and our trust in the tools and in these capabilities, I would say.
Michael or Ritesh, any perspective there to add? Or
Yeah, so explainability is one area we've really focused on and we're continuing to build out. So for example, we didn't show it in this presentation, we have the ability to retrieve similar times we've observed in the past where the transmission at the network behaved the way we expect it to behave for the period of inference. So that way we can pull in all the input and the output signals from previous times that we've observed and show that to the final decision maker, for example, in this case, in terms of how much resource to buy, to help generate trust and confidence, but also enable the human, if needed, override some of the outputs we produce, because we have explainability built into the model. So that is a core principle as to how we're building these tools. And the goal is over time to actually build this into an application where it's very intuitive to make sense of all the explainabilities outputs that our model can generate, so that the humans can make prudent decisions on the basis of the model predictions.
Yeah, I think the thing I'd add is, this is a very empowering technology rather than a disrupting technology in a lot of ways. And, it's about gaining trust as we go. Like, the conversations are about power system conversations and looking at results. It's very data rich and visual, and we've put a lot of effort into the explainability, the visualization, the ability, if you see something, say, well, what if this, what if that, let me see this variable. And for power system experts, in some way, our experience with EirGrid was they enjoyed it, and the chance to dive deeper and maybe get some understanding of a problem that they understood well, but to test out ideas they had that maybe other tools wouldn't have let them maybe test or to validate and to understand. And I think as you go through that sort of process, you build trust and you understand it. I think as well, like, trust is a thing. Like, a lot of the existing tools, don't give good functionality into a lot of these areas where you're trying to do very complex forecasting, maybe 24, 48, 72 hours in advance, and you're not really sure what your operating schedule is going to be, what your optimal battery charging view is. And I think this is going to give you way, way better views than anything else out there at the moment. And that then gives you a basis to go and if you want to do a sanity check or run it, you can use it to do it. I think as the technology matures and a few years down the road, you're going to see it getting closer into real time and more operational goals. But a lot of our focus at the moment is in the day ahead planning, because it sort of gives the operator a chance to give them more usable information. Uncertainty is high, where the model can fill a big gap, but it also gives the operator time to think and to refer, use this in a thoughtful way to help to essentially have a more efficient way of running the grid. So I suppose the summary is, look, this is about a partnership. It's going to change a lot of things over the next few years in how power systems are operated, how grid operators run, and our philosophy is to do that in a collaborative way where we build the insight and we gain that confidence and knowledge together with the people that are using the tools.
Great, thanks. So we're at the top of the hour. I want to respect your time. I know it's getting late in the evening for you three. So really appreciate taking the time presenting today. I mentioned we'll share the video file, and I think we'll try to get to some of the questions on here too, if we can answer them offline and share that with the file. So appreciate everyone's participation. I also want to give a plug-in that folks, well, hopefully you can join these webcasts in the future, but also the ESIG Fall Technical Workshop, October 27th through the 29th in Philadelphia, Pennsylvania. We'll have a panel on AI applications, or putting AI into power system applications. So we'll have some additional case studies there from some system operators. So I think that'll be really good, and sort of a follow-on to what we talked about today. Michael, Ritesh, Owen, I want to thank you again for the webinar, and for all our participants for joining in today and asking lots of really good questions. Look forward to seeing you all again, and take care, stay safe. Thanks again for your participation. See you all.
Thanks, everyone.
Thank you.
Thanks.